Hello lovelies, hello all. So today I thought we would do a bit of electron configuration. It's super easy, but at the same time can be extremely complicated if you have a shitty teacher. But luckily for you, I am not considered too shitty. Hello Regina, hello. Hope you guys can hear me. Cool, yes? Okay. So I thought we'd do some electron configuration, looking at the 3 rules of electron configuration, and just me generally explaining what it means. A lot of times people just parrot fashion learn electron configuration, but it doesn't stay there when you forget these things. So you have to understand it to actually remember it. That's what we're going to be doing today. Okay, so everybody, when we start off here, electron configuration, okay, what we're talking about is we're referring to atoms, right? When we're referring to an atom is going to be made of protons, neutrons, and electrons. Now, protons and neutrons are easy enough to draw because, as we can see here, we're just going to be drawing little dots in a center, right? And that's the nucleus of an atom. That's fine. But to draw electrons is a bit difficult. So electrons are a bit more complicated to draw because what we like to do is put these energy levels like this. And we know that the further away from the nucleus we get, the energy is going to increase. And why is that? We're talking about the energy of the electron. Okay. So the further away from the nucleus an electron will get, the less interaction there is between the nucleus's positive charge and the electron's negative charge. So as we're sitting in the first level here, it's stable. But as it gets further out, as our levels of shells, as our number of shells increases, the energy of those electrons is going to increase. But in this case, if we're saying that protons are red, okay, that means that we're going to have 1, 2, 3, 4, 5, 6 electrons. Okay. Now, the first energy level is going to contain a maximum of 2 electrons. So right now, it would be something like helium. Okay. Anything more, and it's going to have to go to the next energy level. You see that? So each energy level only contains a certain number of electrons. So this is the first energy level, number 1. Okay. We refer to the energy levels as N. Now, this is where your teachers might stop, and I'll carry on. Okay. When it comes to energy levels, you got to understand that it's not so much that they are in a line and that they are spinning in a line. It's not so much that they are spinning in a line around each other like a track. It's more like there are areas, bands, okay, like thick areas around it where electrons could be. And it's those bands that form the levels. So the levels shouldn't really be considered, this line is 1, this line is 2. It should be considered, if you want to think of it as in actuality, it should be considered as this band over here is number 1. And somewhere in that band, there are 2 electrons that are spinning around in that area. Again, not spinning around in one line, but just in that area, somewhere, the probability that there is 2 electrons. That's how the more realistic idea of electron flow and electron configuration looks like. Okay, but just for sake of explaining a bit easier and understanding this stuff, we'll refer to it as these lines. But just think of these lines as thick areas instead of just a single track line that the electron will float around on. Okay, so N equals 1. Now we have 1, 2, 3, 4, 5, 6. We have 6 protons here. So we can say, so in this case, P equals to 6. So our number of electrons in a neutral atom is also going to equal to 6. So once that first energy level is, we can say maybe saturated with electrons, okay, we're going to go to the next energy level for the rest. So 1, 2, 3, 4, 5, 6. Okay, now notice how I drew those. It's very important, okay, and it's going to come up later on, and it's good to just get in the habit. But what you're going to do is you're going to draw them on each, we can say, side of the electron first. If, however, this had 7 protons, and I had to draw another electron, I would go 1, 2, 3, 4, 5, 6, 7. You see that? So these electrons are going to be in pairs, okay? But only when the orbitals, they're called, are going to have 1 electron in each. When I was talking about these areas that electrons can occupy, we refer to these areas as orbitals, okay? And depending on the level that you are on, it's going to have different orbitals, okay? And you have sublevels as well, but we'll get to that. Okay. So the first level we call number 1. 1 has only one sublevel that we refer to as S, okay? So We can call these sublevels. Now this is where it gets a bit different to who explains what here. Yeah, okay. So we refer to these things, I refer to them as sublevels. Some people refer to them as subshells, but I like to refer to them as sublevels. So n equals to let's say the shell. So in this case, shell 1. And then in n, in each shell, you're going to have these subshells. So the subshells are going to equal to S, P, D, and F. So these are the subshells, and it actually carries on going and going and going and going, but we'll just stick to S, P, and D probably. Okay, it gets a bit more complicated as you get higher, but it's okay. So n equals our number of shells, okay? The subshells are S, P, D, and F. Now, in those subshells, and remember this is what I was talking about, so within these layers that we call shell 1, okay, they're going to have orbitals within them. Just bear with me now. This is part of the thing that you just have to remember as well. Okay, so this is going to have, we can say, orbitals. S has 1 orbital. P is going to have 3 orbitals, while D has 5 orbitals, but 7 is going to be the number of orbitals. Okay, now our number of electrons per energy level. Guys, I used to teach this, and I used to have a formula. I can't quite remember it now. Maybe we'll figure it out today. But there was a formula to figure out the total number of electrons in each shell. Does anyone know that formula? Because what's going to happen is that for each orbital, we're going to have E minus, we're going to have 2 electrons in each orbital. Okay, so P can have a total of 6, D can have a total of 10, F can have a total of 14. Okay, now on top of electron configuration, there is a certain, what do we call it? Order, rather. So an order that we're going to put these subshells in. Exactly. Was it 2n squared? So 2n squared, did that calculate the total number of, let's see here, 2n squared. That might be the total number per level. But we'll look at that now. Thank you, Regina. Let's have a look at it. Okay, so if our number of shells, let's say, in this case, okay, what we've got here. If I had to tell you to do the electron configuration, well, first it would help if we said, okay, this is actually going to have 7 electrons and P is equal to 7. Okay, cool. So firstly it would help to know what element we're looking at. So we're looking at nitrogen. Now, if I had to ask you, what would the electron configuration for nitrogen be? I'll give you guys a second to see. What would the electron configuration for nitrogen be? You can type out your answer in the comments. I know, listen, number 1, it's there. See there? Immunity. I've got it written down. Today I'm just feeling a bit sick, and immunity was a big topic. So voila, tomorrow I will do immunity for you. Okay. Today I just thought my nose and my brain are way too foggy to do immunity. It's quite a big one. Okay. Okay guys, what's the electron configuration for nitrogen? Does anyone know? So the total number of electrons is going to be 7. So that means that it would have to fill the first level first. And that first level is going to be 1s. 1s is going to take 2 electrons. Let me actually draw it like this. So now this is what we're going to something called the Aufbau diagram. Okay, so our electron configuration can be 1s squared, because that shows how many electrons we have. Let me actually do it here, but okay, so if we were looking at nitrogen, I hope you guys have written down the electron configuration, what you think it is. So first we're going to have 1s squared, okay? So that 1s, 2 electrons. After that, we go into the second energy level. But the second energy level, and all energy levels, start with S and then go P, D, F, sort of. I'll show you now. But what I'm getting at is that after 1s, we have 2s. S can only hold 2 electrons. So again, 2s squared, that's 4 electrons. Okay, so we're going to need a bit more. We're going to need 3 more. Okay. After 2s, we have 2p. Now P can hold a maximum of 6, but we don't have 6. But we do need 3. So the electron configuration for nitrogen is 1s squared, 2s squared, 2p cubed. You guys got that? So let's have a look now. I want to see if Regina's formula here is right. So theoretically, the maximum number of electrons, is equal to 2n squared. Okay. So let's say instead of nitrogen, this was going to be neon. Okay. So the electron configuration for neon is going to be 1s squared, 2s squared, 2p6. Total number is 6. Okay. The max number of electrons, okay, for the first energy level, let's say would be 2 multiplied by 1 squared. Okay, 1 times 1 is obviously 1, multiplied by 2 is 2. Yes, so for n equals 1, it's going to have a max of 2 electrons. For n equals to 2, the max is going to be 2 multiplied by 2 squared, okay, is going to have a total number of 8 electrons. You see that? So thank you, Regina. That's exactly right. This is our formula that tells us what the maximum number of electrons is in an energy level. Okay, it's going to be 2n squared. And that makes sense because 2s, 2, 2p, 6. You see that? 8 electrons. Okay. And again, keep in mind, when we're talking about these energy levels, when we're talking about 2s squared, 2p squared, it's not talking about the lines here. Okay. Both of these are still, because they are in period 2 on the periodic table, you see them? Here's period 2. Because both of these are still in period 2 of the periodic table, it means that they are going to have 2 energy levels, or 2 shells. Okay, so just because it says 1s2 or 2s and 2p, it still only has 2 shells. And that's why I say it's better if you can think of these shells as bands around the atom, rather than just a line. Because in that band, you can have multiple orbitals, you can have multiple configurations, and multiple different energy levels. So, another way that we can represent this is something called an Aufbau diagram. Okay. Now, these Aufbau diagrams are going to represent the energy levels, how much energy each level is going to have. So, starting out, you have to realize that it is spelled quite whack. Okay, it's spelled Auf. Oh gosh, I can't even remember. I think it's Aufbau, something like that. Is it? Let me see here. I can't remember. Yeah, that's it. Aufbau. Okay. And basically, Aufbau came up with this concept, or not even concept, how it works. And he said that electrons will occupy the lowest energy orbital that will receive it. So Aufbau basically said that when you have electrons, they're going to occupy the first and lowest energy level first. You see that? That's why we did 2 electrons before moving on to the next level. Now that is the Aufbau principle. Okay, so we'll write these, yeah, you guys can see it, but we'll write these over here. Okay, so we can say the rules. So the first one is, I'm going to do it in colors, because we love colors. I like it in black. Aufbau states, electrons occupy the lowest, oh thank God, I thought I wasn't recording, lowest energy level first, before moving on to the next one. So that's the Aufbau rule. So we start out with 1s. Okay. 1s, we know that, no, you guys can't see this, can you? Thank you for the gift. So 1s is going to have s having 1 orbital. Now we draw these orbitals as little boxes because we have to show that inside these little boxes there's going to be 2 electrons per orbital. Okay, because remember that up here we said that in the first energy level we have 2 electrons. It only has 1 subshell, s, and so each orbital has to contain 2 electrons. If there are 3 orbitals, it means there are 6 electrons. So when we break these orbitals down into little boxes, we can show that they have 2 electrons in them. Now, how do we show, okay. How do we show that these electrons are going to be in the box? Well, this brings us to our second rule. Okay. We are going to be drawing them with arrows. Okay. Specifically, arrows going down and up, or up and down. Okay, but the point is you have to show that these electrons are going, yeah, you guys can see this, right? Maybe I need to zoom out a bit. Can you guys see? Is it all okay? Yeah, that's fine. Eh? So, we're going to show that these electrons, they're going to be 2 per orbital, and that they are going to be spinning in opposite directions. So, electrons in an orbital are going to be moving in opposite directions. Thanks for the gift, Eva. So, after 1s, and I'll get to it now. Oh, maybe I will. I think so. That's Hund's rule. No. So that's Pauli's exclusion. Okay, so the next rule we've got is Pauli's exclusion. I'm actually going to write this, exclusion. Pauli's exclusion, electrons in an orbital will spin in opposite, let me write this in opposite directions. Okay. Now you might be saying, oh, my teacher didn't give us a definition like that. There's lots of definitions for this that's happening. But that's basically it. I'm just giving the basics here of what it is. So you could also say no two electrons within an atom may have an identical set of all four quantum numbers. That's another one. Some might even say electrons sharing an orbital have opposite spins. You see, it gets very in-depth, but that's fine too. Okay, now let's go back to nitrogen that we were talking about earlier. So 1s squared. Next one, 2s. And what I like to do, and what you should do, is keep your orbitals in lines. So put all the s's in the middle like this. Okay, because after this it's going to get a bit messy. So 2s, it needs its orbital filled. I don't know why I drew down up first. It doesn't really matter, but as long as you show that they are in different directions. After 2s now we have 2p. Oof, sorry, my nose is buggered. 2p. Now again, different ways of drawing this. I like to just draw it like this, 2p, and you draw your boxes a little offset. And why? Because 2p, p has 3 orbitals. So we have to draw it 1, 2, 3. And as you draw it 3 orbitals, we have to now fill those orbitals. But again, people, this is what I was talking about in the very beginning here. Okay, when I was drawing it, I didn't put these electron pairs together in the beginning. I made sure that all of the sides were filled before doubling up. And that's what we do in the orbitals. We have to go, okay, well, how many more do we need? We need 3 more. This thing isn't going to work for that. But yeah, so this would be nitrogen. 1, 2, 3. You see that? So only once all 3 of these orbitals has been filled, can I then go, get out of here, these people are trying to co-host. Only then can I go back now and fill it up if I have more. So let's say this was for neon. If this was for neon, yeah, so this is nitrogen as it is here. Okay. If I was to do it for neon though, neon is going to have 3 more. So I would draw here 1, 2. But only once each of these boxes is filled with at least 1 can I go back then and put in more electrons. Okay. But right now I think we'll keep that for nitrogen. I actually want to do oxygen. So we're going to change this back a bit. Actually, we're not going to. I'm just going to add another electron because we can do that, right? I can say this is no normal nitrogen atom. This is going to be nitrogen minus 1. This nitrogen is going to have a charge of minus 1. Let's say this nitrogen. No, okay, so it's just going to have a charge of negative 1. Let me say. So that means that this will have to be, if it had a charge, what can I do this in? Purple. I think, yes. If it had a charge of minus 1, it would be 4 over here. And therefore, if this was nitrogen minus 1, it would have a charge of, boom, I can put it over here. Now this brings us to Hund's rule. So Hund's rule, I'm sure they put it a bit more eloquently than I can, but basically what Hund's rule is saying is that all of your orbitals have to have at least 1 electron before doubling up, before they pair. Okay, now a better way of saying that would be electrons will occupy all empty orbitals in a subshell with a single electron having parallel spins before entering half-filled electrons. Ooh, sorry, my nose is terribly stuffed today. Okay, I think actually I have a bit of marker. 1 second guys, let me just blow my nose. Every time you send me a gift, my nose gets stuffier. That's what this stream is about. It's about me losing my brain out of my nose. Okay, so Hund's rule. Every orbital in a subshell must be filled with 1 electron each, spinning in the same direction. Okay, we can just write there before opposite directions are added or something like that. Opposite directioned, yes, maybe I'm making that word up. Directioned pair is added. Okay. So we've got Aufbau, which says that electrons must occupy, I think I butchered that spelling, occupy the lowest energy level first. So starting at 1 and going up from there. Then Pauli's exclusion, electrons in an orbital will spin in opposite directions. And then Hund's rule that when we reach these bigger orbitals or these bigger subshells that have multiple orbitals, each orbital must be occupied by electrons spinning in the same direction before we can pair them up with the opposite direction. All good? Neon is our last one. Okay, if we had to talk about neon now in this Aufbau diagram, neon would be something like this, right? Because neon is 226, 226. Okay, neon's easy. Now, what if we had the next energy level? Because after neon, we're going to have sodium. Okay, So if we have to look at sodium, I don't think you guys can see this, can you? Yes, Kenzie, Polly. I think Kenzie was actually there in person when I was teaching this. Maybe not, though. I think he might have been too low grade at the time. So, can you guys see here? Yes, you can. So, let's look at sodium. Okay, sodium is going to have 11 electrons. Okay, so it's just one more than neon. So, it's going to be 1s, 2s2, 2p, 6. Now, after 2p comes 3. But 3, so 3 is 1. You see that because neon only has 11. This is 6, 7, 8, 9, 10, 11. Okay, so that would be neon. When drawing it, again, I would like to say, keep them in line. Okay, so 1s is going to have just one more. Okay, that would be neon, right here. Sorry, not neon, sodium, Na. Okay, so that would be sodium. Easy enough, right? Now let's make it a bit bigger. Let's say we do something like silicon. Okay, now silicon being a bit bigger is going to be Si. It's going to have 1s, 2, 2s, 2, 2p, 6, 3s, 2. Silicon's electrons are going to equal to 14, by the way. I'm going to try to keep up that in my head. So right now we've got 2, 4, 6, 12, 3p, 2. So 3p, 2, 3p, and it's important to know we do still draw out all of our orbitals in the Aufbau diagram, okay? And it's going to be 3p. Now notice we have to complete this S before going to 3p, and we have to put 1 in each one before we start adding them up. You see, so I'm not allowed to just put them like this, right? That only really works in the S's. When you go into the p subshells, okay, or the suborbitals, you have to put 1 in each orbital. Okay, and actually same thing for the S. S just has one orbital, so that's why we can just double it up straight away. But when you have multiple orbitals, you have to put 1 electron in each one beforehand. If this thing got huge, what if it got really big? What if it got to 4 levels big? Let's have a look. Okay, so moving down the periods now. Oh, sorry guys, and remember, this is going to be increasing in energy. Now why this is important, unfortunately I'm about to break your minds, and I hope it makes a bit of sense. But as we increase this energy, sometimes it will, how can I say this? The electrons will go to the next energy level before finishing the previous's energy level. And I'll show you what I mean by that. Okay. And this is why we use this diagram over here. We used it last week as well. Where did I put it? Yeah, this one. Okay. So we are going to be looking at the order that electrons will fill, and the order of it's basically the order that electrons will enter these energy levels. Okay, so we start with 1s. We know that 1s. Okay, after that we got 2s. We know that. After 2s we got 2p. Now this is how you guys write it out. Okay, nice and easy. 3 is going to have 3s, 3p, but it also has 3d. Now 4 has 4s, 4p, 4d, and it has 4f. Okay, now this is where it becomes a little strange. So when we're drawing these energy levels out now, we know that it goes 1s. So cool, we start with an arrow like this, 1s. Great. After 1s, we've got 2s. After 2s, we've got 2p, 3s. Great. Now this is where it gets a bit strange. After 3s, we draw another line. It's going to go 3p, but then it's going to go 4s. You see that? So after 3p, it goes 4s. Then it goes back to 3d and goes to 4p before going into actually 5s. So this is where it gets a bit funky when you're trying to draw these boxes, or when you're trying to draw this electron configuration. This is where it gets a bit weird. So after this, let's say it was something, and this is a question they might ask. They might give you an Aufbau diagram that looks something like this. Okay, what's so good? Let me just scope something here. So they might give you an Aufbau diagram, and they might say 4s, and that 4s is filled, and then they go 3d. And D, I again like to just put them a bit separate. 1, 2, 3, 4. Damn it, rules. Get out of here. 5. 3D. 5. But let's say it only has 3 electrons. Actually, I'm going to make it, just to show Hin's rule a bit, And remember guys, I'm just putting it in this color so that we can see Hund's rule in action, but it doesn't have to be, it'll be in the same color. Then I'll ask you now, what atom is this? What element is this? Copy this out now. Okay, if I have to count out rather. No, there's 27 electrons here. 27 electrons. Let's say there were 27 protons. It's going to be cobalt. CO. So the answer here would be CO. Ooh, not that big of an O. Oh, yo, this stuff really, I'm bleeding. It's going to be cobalt with 27 electrons. Okay. Interestingly enough as well, if we had to say, okay, what is the max number of electrons when n equals 3? It's going to be 2 multiplied by 3 squared. So that's going to equal 18. Okay. And that's because 1, how can I write this? Now, yeah, guys, this is where I say, these notes are cool and all, and I can imagine they are nice summaries, but you have to do this yourself. You have to make your own summary notes when it comes to this. Okay, take this. Can you explain equivalence bond theory? Sure, I can try. Equivalence bond theory. Let me write this down so I can see. Equivalence. Guys, so I just wanted to write here that n equals the subshell. Okay, so maybe I'll make it over here. Just a little summary quickly. So when n equals to 1, the subshells is going to equal to S. Okay, when n equals to 2, subshells are SP. When n equals to 3, subshells are S, P, and D. When n equals to 4, it's S, P, D, and F. The orbitals, so we can say here the number of orbitals. S is going to have 1 orbital. In this case, this is going to have P and S, so it's going to have 4 orbitals. Okay, this is going to have, let me see here, 1, 4, and 9 orbitals. Someone calculate this for me, someone in my OGs. How many orbitals? If it has S, P, D, and F, how many orbitals is that going to have? Anybody? Okay, and then the total number of electrons is going to be 2. In in 2, we said it's going to be 8. In 3, we said it's going to be 18. In 4, it's going to be 4 squared 16. It's going to be 32. And the total number of electrons we're using is 2n squared. To calculate the total number of electrons. Okay. The total number of orbitals, is that going to be 16? 9, 10, 11, 12, 13, 14. No shit. Go. 3, 1, 5, right? 5 and 7. Okay. 12, 13, 14, 15, 16. Cool. So the total number of orbitals is going to be n squared, which is cool. And the number of subshells is just going to equal to n. Great. Look at us. See guys, this is how you make summaries. If you can remember this now, just these. Okay, it'll save you so much more. To make a little. There you go. Oh man, I could have made that straight. I could have, but that would be boring. This is electron configuration. A whole month-long topic that is taught during schools because it's extremely difficult to teach in a class, but I'm going to teach it to you in under 10 minutes. Okay. So, when it comes to electron configuration, what we're looking at is where in an atom we're going to find electrons. What is the structure of their motion? That's electron configuration. So we know that electrons are spinning around an atom. We also know that electrons that are further away from the center of the atom are going to have more energy. Okay, so the distance from the center, we're going to define them into shells. Okay, and these shells are going to just be numbered 1, 2, 3, 4, 5. Okay, but within those shells, we are going to have subshells. They're like sub-areas of that shell. So that's why I always say it's important to know that when we're talking about a shell, it's not just one line, it's a thick area. And inside that area, we have subshells. We have sub-areas within there. Okay, now the subshells that we're going to get, we refer to those subshells as S, P, D, and F. The bigger the shell, the more subshells it's going to have, obviously, right? And the bigger the subshell, the more orbitals it's going to have. So within those subshells, they're going to have different conformations and different shapes that those electrons are going to be spinning in. You see? And so if they're spinning in different shapes, the bigger the shell, the bigger the energy, the more shapes they're going to be spinning in. So starting at energy level 1, okay, it only has one subshell of S. Okay, that one subshell of S is going to have one orbital. That one orbital S can hold a maximum of 2 electrons. Okay? And those 2 electrons, okay, are going to be spinning in opposite directions. That is Pauli's exclusion. Okay. Now Aufbau made this diagram, okay? And he based it off of the fact that electrons are going to occupy the lowest energy level first. Okay, so starting at 1s, that's the lowest energy level. If you have more electrons than just 2, it moves to the next energy level, and the next, and the next, and the next. But sometimes it doesn't just always go 1s, 2s, 2p, 3s, 3p, 3d. There will be energy levels, how can we say it, like before others, okay? And that's where we use this pattern over here, okay? And we draw these arrows down here to sort of understand which energy levels have more energy than others. So something like 3 or 3D, even though it's in the third energy level, it has more energy than 4s. And therefore, 4s has to be occupied first and fully before we can start putting electrons into 3D. That's the point of this. Okay. So if we are looking at something like cobalt has 27 electrons. You're just going to draw them, and you're going to move up the energy levels. Eventually, you're going to get to one of them. And again, just get in the habit of when you're writing out the electrons in these 2p, 3p, or 3d, something like that, do it one in each orbital before doubling up. Just so it becomes a habit, so that you don't double up by mistake one day before occupying every orbital with at least one electron. And that is Hund's rule. Okay, so here are some of the formulas that you have to know, or you don't have to know them, but it makes it a lot easier. So the shells, 1, 2, 3, 4. The number of subshells depends on just which number of shell you're in. So 1 is going to only have one subshell of S. 2 has S and P. 3 is P and D. 4 is P, D, and F. Now n squared is going to be the number of orbitals. So that's going to be how many orbitals are going to be in each subshell. So S only has 1. P is going to have 3. And because it has 2 subshells, S and P, it's going to have a total number of orbitals of 4. Now this 1, 3, and D is going to have a total number of 5 orbitals, so it has 9 orbitals in total. You see that? And 4 is going to have 16. Now the total number of electrons, each orbital is going to have 2 electrons. You see that? So it's going to be 1, it's going to have 2 electrons, first one, maximum of 2 electrons. S and P is going to have a maximum of 8 electrons, because it's going to be 6 electrons in P and 2 electrons in S, and then so on and so forth. But the formula you can use is 2n squared. Boom! I don't even think that was 10 minutes. Okay, I hope you guys all understand this. I'm going to bounce, because I'm going to go have some lunch.